Mhm. Hello.
Yes, we are about to start.
Okay. Thank you, madam.
Okay. Okay, so good evening, everyone. I welcome you all to the second tutorial of this course, which is Reagents in Organic Synthesis. I hope I am audible to you all, and I will quickly share my screen. So, in last week's tutorial, which was the first tutorial of this course, Reagents in Organic Synthesis, uh, by NPTEL, whose course instructor is Professor Subhash Chandra Pan from IIT Guwahati. We discussed various reactions and important examples on oxidation reaction chemistry. Okay, and there mainly we solved questions on chromium reagents, sulfur reagents, and also organic peroxides. So I hope my slides are visible to you. I'm just going to start today's tutorial. In between, I'm also going to ask you a few questions. If you are able to answer, please answer. And if you have any queries or any doubts regarding the slides or the questions that are going to be discussed, don't hesitate and ask me, okay? Because I'm there to help you. I'm your PMRF teaching assistant, Deepika, and I'm pursuing PhD in chemistry at IIT Bombay. So, okay, we're good to go. Let us start with the second tutorial of this course. Also, one more thing. Actually, in last tutorial, some of you asked me about easier books on this course, okay, and preferably Indian authors. Some of you were asking me about books, reference books, which are uh, written by Indian authors. So I personally did not have much idea about Indian authors' books. So I discussed the issue with my supervisor, PhD supervisor. So he has asked me to suggest you that it is better to follow books like Claydon, Caruthers, and if you are finding those books difficult, then you can choose this particular book, Organic Chemistry by Stanley H. Pine. These books, my sir has said that this book consists the topics in an easier language. Okay, so you can follow this particular book for this topic, Organic Chemistry by Pine, because there are a few books by Indian authors, but those are not very popular and not much followed because there are many mistakes contained in those books. Okay, so better to follow the standard chemistry books. Otherwise, you will learn some mistakes from the books which are containing mistakes, and just go through Pine, and also Carithers and Claydon are there already. And one more suggestion I can give you that when you are watching the video lectures provided by Professor Subhash Chandra Pan sir, you can uh, take a notebook along with the video and you can write down whatever he is saying, and you can write down the reactions as well. If you do that, your own lecture notes will be ready immediately. Just if you are feeling that he is speaking a little fast, you can just pause the video then and there and then write down what he said. That will help you to get the correct informations. Okay, rather than following any random books on the topic, you can just make your own lecture notes. That will be very, very helpful. So that is the procedure that we follow when we have to prepare for competitive exams like CSIR NET or GATE. We make our own lecture notes, so that also will be very helpful. Whatever video lectures are available by Professor Pan sir on YouTube or on NPTEL website, you can just make your own lecture notes. That will be the most helpful way. So with this, let us start with our today's topics. So in second week lecture series, we saw videos on some more oxidizing agents. So we are going to discuss some easy and difficult questions on the same topics. So this is the first question of today's tutorial. Okay, if you have any query, just let me know. So you are given an organic molecule here, and you can see you have a bridged oxygen, a cyclic ether functionality here, as well as OAC, like acetyl protected oxygen, benzyl protected oxygen, as well as TBS, that is silyl protected oxygen functionality in the molecule. So this is highly functionalized substrate. So at the first glance, you may get scared looking at the substrate that, oh my God, there are so many sensitive functionalities are here, like acetyl, benzyl, or silyl. Oh, like in the first tutorial also, I told you that O-silyl bonds are very, very sensitive to acids and bases. Okay, especially whenever it comes in contact with acid, this OTBS group can fall off very easily. So you may think that if we treat this substrate in our reaction with selenium dioxide in presence of hydroperoxide in DCM, what product we will get? So luckily, selenium dioxide is a reagent which will selectively oxidize your allylic position. Okay, it is marked already here, and in the video lecture also, in the first lecture also, you might have gone through sir's reactions as well. He has also taught that selenium dioxide preferably oxidizes allylic positions. Okay, but he also mentioned a few examples where you could see how the reactivity was dependent on steric hindrance uh, and other reaction factors. Okay, so please go through all the examples which are covered in the lecture as well. Okay, these are just some additional examples which we are going to solve today. So if we revise the mechanism of selenium dioxide oxidation, you will see when you have an allylic carbon. Okay, so you have, suppose we are oxidizing this position. At first, the oxygen from selenium dioxide would extract this hydrogen to give you an exo carbon-carbon double bond. So in this intermediate stage, you will see the change of the double bond position from endo to exo. And this particular intermediate is called allylic selenic acid. Okay, so after this acid is formed, this is not very stable and it immediately undergoes 2,3 sigma-tropic rearrangement. Okay, this bond, this carbon selenium bond would break immediately and give you 2,3 sigma-tropic rearrangement to give you again the endo carbon-carbon double bond. And finally, this oxygen selenium bond will be hydrolyzed and you will get the desired product, which is allylic alcohol. Thus, selenium dioxide, if you recall, manganese dioxide and selenium dioxide both prefer allylic position whenever it comes to oxidation. Okay, if you have allylic and non-allylic positions, always go for the allylic position for oxidation. And this is the general mechanism which have been already taught in the video lecture. So thus, the initially given substrate which were containing so many sensitive functionalities, you do not worry, just simply oxidize the allylic position. If you look at the other side of the double bond, here also you have allylic position, but you do not have a proton for abstraction at the first step. Okay, so this side oxidation will not happen, only this side oxidation will take place, and you will get this allylic alcohol as the product. And if you see, the yield of the reaction is also very good, which is 93%, and reaction conditions are mild. So whenever we have such acid sensitive or base sensitive reagents and you want to oxidize particularly these allylic positions, the organic chemists always choose selenium dioxide as it is giving such an excellent yield. So this was an easy question, I guess. uh, Let us move to the next question now. Okay, so again, another question from selenium dioxide oxidation. Here, the products are already given. Okay, again, if you look at the substrate, you can see a lot of functional groups which are reactive. Like, for example, you can see this OTMS. OTMS group, whenever you have in the substrate, you have to be very careful, because in very dilute acidic solution also OTMS group can fall off to give you OH, which means oxygen silicon bond easily breaks in OTMS group. Okay, so apart from OTMS group, you have alcohol here, and then you have this anhydride functionality, and then you have two ketones. Okay, these two ketones also are present. So if we treat this uh, highly functionalized tetracyclic molecule with selenium dioxide, the same condition as the previous reaction. Okay, here I have already given you the products. In one side we can see oxidation at this position, and on the other side you can see oxidation on this position. You get this one allylic alcohol, and the other you get is this one. Okay, so now the question is, which out of these two will be the major product? This one or this one? Yes, can anyone guess?
First,
Yes, first one is major product. Why is it so?
because from bottom side the TMS group is sterically hindered.
Yes, what is your name? May I know?
Sharad,
Okay,
Sharad.
okay, Sharad. Very good, very good. That means you have already gone through the lecture and completely understood, well understood the concept. Yes, like Sharad said, that first one will be the major product. Why? Because the first, this in the second one, if you see, this allylic position is closer to this OTMS group. Okay, due to which, if we compare the steric hindrance experienced by the allyl positions, you will see that this position is sterically free and more exposed to react with selenium dioxide. Okay, this position is sterically free. This is why oxidation at this position will follow very easily, and thus you will get 61% yield of the first product and 38% of the second product. And like we saw in the first reaction, OTMS group is intact. It will not fall off upon reacting with selenium dioxide, and also all other functionalities will stay intact. And one more thing, if you notice, you have another tertiary alcohol here, okay? That is also kept intact and untouched by selenium dioxide, because selenium dioxide is very, very selective for the allylic position. So if you get such questions in come across such questions in literature or exams, you just remember the selectivity of selenium dioxide and also the steric preferences. Okay. Of course, if you use excess of selenium dioxide, then maybe you can change the ratios, but in case of standard conditions, you will always get 61% yield of the first product. So with that, let us move to another easy question, uh, which is from the TPAP oxidation part. Okay. So tetrapropyl ammonium perruthenate, a ruthenium complex which is used to oxidize alcohols. Okay. And this reagent, particular reagent TPAP, is known to be very, very mild, and it is, I have seen that this reagent TPAP is used by a lot of organic synthetic chemists whenever it comes to total synthesis. Because what happens in total synthesis of natural products, in the natural product you have a lot of sensitive functionalities, okay? And chemists prefer this particular reagent TPAP over DCC, PCC, etc., because this is believed to be very, very mild and it never disturbs the other functional groups. It only goes for the oxidation of alcohol. Okay, always remember. And the reaction is called Lay-Griffith oxidation, where TPAP reagent oxidizes the alcohol. If you recall the mechanism of the reaction, at first what happens, the perruthenate anion of the reagent will take up the acidic proton of the alcohol to give you oxyanion. Okay. So at first, ruthenium is in +7 oxidation state. Okay. And at the end of the reaction, you always have to remember ruthenium gets reduced to +5 oxidation state. That means 2 electron transfer is happening in the overall oxidation reaction. So in the first step, like I said, the perruthenate anion will take up a proton from alcohol, and then the oxyanion uh, will in turn attack the ruthenium center. And if you look at this arrow, you form another oxyanion at the perruthenate center. So that oxyanion which is newly formed will take up this alpha proton of the alcohol, and in turn you will get a carbonyl compound. So thus when you have a secondary alcohol, this Lay-Griffith oxidation will always give you ketone, and since it is a metal complex, we will always want to get it back so that we can reuse it. So in this oxidation reaction, NMO is used to reactivate the catalyst, so that we can cut down the expenses of the reagent. Okay, like we do in the osmium tetroxide oxidation also. So in Lay-Griffith oxidation as well, NMO is used and methyl morpholine is used to reactivate the catalyst, and methyl morpholine oxide, this one. Okay, so at the end of the cycle you get your catalyst back, and then this catalyst is ready for another cycle. So like we saw in the mechanism, in this particular substrate where you have epoxide which can be easily opened because of its ring strain, and you also have an ester functionality here, you need not worry even this diene will not react or rearrange. You have to simply go for the oxidation of the alcohol. Okay, TPAP is very good reagent for selective oxidation, and you will get aldehyde at this position. Also, if you look at this note, you can see 12% in sworn oxidation. So the researchers who carried out this particular oxidation, they observed only 12% of yield in sworn oxidation, maybe because of the presence of other functionalities. Okay, maybe opening of this epoxide ring happened in sworn oxidation, which could give you undesired products. Okay, but TPAP is chosen for this particular reaction, which gives you 78% of yield. So after covering selenium dioxide and TPAP, let us move to another oxidizing agent which was discussed in the lecture 2 of this week, which is Fetigens reagent. So Fetigens reagent is nothing but silver carbonate and silicate, and it is called Fetigen because two chemists developed this reagent, one of which was Fetigen, and after his name, this name of this reaction is given, which is Fetigen's reagent. Okay, and it is particularly used for oxidation of alcohols. And if we talk about the mechanism, it mainly involves adsorption chemistry. Okay, so what happens when we are putting the alcohol with silver carbonate on silicate, chemisorption of the alcohol happens. Okay, so after successful adsorption, electron transfer reactions happen, and at this position you can see you get a radical cation. Okay, because silver is extracting one electron from this side and the other electron from this side, and you get carbon's hydrogen bond breakage, and at this oxygen atom you get radical cation. This radical cation quickly undergoes further deprotonation, and you get combination of carbon and oxygen radicals to get this ketone. Okay, so this is the simple oxidation reaction mechanism of Fetigen's reagent, and you just have to remember that wherever you are seeing alcohol, you have to go for that one. But in these examples, we will see various selectivities of the reagent. Okay, what if we have only one equivalent of the reagent that cannot react with both the alcohols, right? If we have in excess amount, both the alcohols can react, but if we have limited amount of silver carbonate, only one equivalent of silver carbonate, that will always react with only one alcohol. So you have to note down that whenever you have primary versus secondary alcohol under Fetigen's oxidation conditions, the reagent will always go for the secondary alcohol. Okay, it is selective for secondary alcohol. One more thing you have to remember, if you have two secondary alcohols, like you see in this substrate, if you have two secondary alcohols, even primary also you have in this one. Okay, but like I said in the first reaction, if you have primary versus secondary, you have to ignore the primary. So this alcohol we will eliminate at the first step. Then you are left with two secondary alcohols. In this case, you have to know the other selection rule. When you have more than one secondary alcohol but only one equivalent of silver carbonate, which of these two alcohols will react? Can anyone answer to this question? Which of these two will react?
Standard alcohol will react first.
Yes, but since we have two secondary alcohols, which one of these two will react?
Middle one.
Below one?
This is
Okay.
yes, madam.
Why is it so?
Because this alcohol is allylic position.
Yes, yes. Very good. What is your name?
It's like it is Subarati, madam.
Okay. Yes. Um, you are correct, and very very good that you have understood that the selectivities, like Mr. Reddy has answered that in between both these two secondary alcohols, the allylic one will be preferred by silver carbonate, and you will get this alpha beta unsaturated ketone. So you have to note down these points, okay? Because if you are given only one equivalent of the reagent, you have to choose the alcohol which is the most reactive towards the reagent, okay? See, if you have only one alcohol which is primary and no other alcohol, then you will oxidize the primary one. Then if you have primary versus secondary, you will oxidize the secondary one. But then you have two secondaries, which is one of which is allylic and the other is non-allylic. You have to go for the allylic. So these points you have to understand. And if we talk about the reason why this allylic is preferred, then you can understood as, see, this carbon carbon double bond is planar, okay? So this planar phase will be chemisorbed, will be absorbed on the silver surface very very easily. And when this planar surface is very very easily absorbed on the silver surface, this particular alcohol will be closer to the silver surface, okay? So this is why you can guess that the allylic position is preferred. Then we have another reaction. By mistake I have already shown you the product, but let us go step by step. You have this diol this time, okay? There is no selectivity this time because both are primary, and it is a symmetric alcohol if you look at it. So this diol is treated with silver carbonate in silite, and the reaction is carried out in benzene reflux. So what happens when you are given only one equivalent of silver carbonate? Any one of these two alcoholic functionalities will be oxidized. Any one of these. You can oxidize this one as also and this one also, because it is just symmetric. Any one alcohol you can oxidize. So you will get this aldehyde, right? If you write the aldehydic functionality on this side also, that is okay. Just do not oxidize both the alcohols because you are given only one equivalent. If you are given more than one equivalent, then the reaction will mention that excess reagent is given. Okay. So we have oxidized one alcohol to its aldehyde form. Next, what happens? As the attack of this alcohol on this aldehyde will give you a six-membered lactone, then the reaction will immediately undergo this cyclization reaction. This is because of the formation of a stable six-membered ring. Okay, whenever you have a substrate like this and you have a possibility of forming a five or six-membered ring, then you have to know it will always undergo cyclization. And these cyclization reactions sometimes do not happen at room temperature, okay? But your condition is already reflux, and this reflux condition will be definitely more than 80 degrees, okay? So thus you have to understand that when you have such a harsh reaction condition and you have an option of forming 5 or 6 membered rings which are very very stable, this alcohol and this aldehyde will undergo lactol formation, hemiacetal formation, and then you can expect if you add another equivalent of silver carbonate, you will get this lactone as the final product. So this kind of reactions of diols are observed whenever you have silver carbonate, which is Fattigen's reagent. Okay. So in diols, you can expect various products. Sometimes when you initially use excess silver carbonate, both these alcohol functionalities can be oxidized as well. Okay. So, but when you add step by step, you first oxidize one of these two and then ring closure happens to give you lactone product. So, these were the questions from the topic Fattigen's reagent. Okay. And this particular reaction has been covered in the week 2, lecture 2. Lecture 2. Okay. If you have any query, you can also visit the second part of the week 2 lecture 2. Then we have this particular reaction. So this reaction is a little different from what has been covered in the video lectures. Okay, this reaction I have included just to show that how ferric ammonium nitrate on silica can behave in some particular reactions. Okay, the basic reactions have already been covered in the week 2 lecture 1. Okay, how ferric ammonium nitrate give you oxidation reactions, and sometimes it gives you aromatization as well. Okay, but in this particular reaction it has participated as two participated in two roles. Okay, this is why I have included this example. So let us go through the reaction mechanism. So when you take this amide, okay, and you treat it with benzaldehyde in presence of ferric ammonium nitrate, what happens? We already know that amines with carbonyl compounds give us hydrogens. Okay, so at the first step, if you see ferric ammonium nitrate, that is cerium metal, is behaving as a Lewis acid which is activating the carbonyl group. Okay, it is activating the carbonyl group of the carbonyl compound, which is aldehyde here, and because of this activation, the hydrogen formation reaction is faster. Okay, so in the first step, you will see this imine formation, and then in the second step, what happens? You can see the enolization of this carbonyl group. Okay, and after that, this whatever enolized product we got, that will attack at the imine generated at the first step. So this step is giving you ring closing, leading to the formation of this 6-membered newly formed ring. Okay, and at this particular step, cerium is coming again to act as an activating as well as oxidizing agent, and finally cerium reagent will give you your product, which is this one. You may find this whole process a little difficult, but you don't have to worry. I only have included this example to show you that ferric ammonium nitrate not only acts as an oxidizing agent, sometimes when you have carbonyl compounds, it also activates as the carbonyl groups as a Lewis acid, and it accelerates rate of the reaction, such as imine generation reaction in this example. Okay, you do not have to memorize anything in this one. You just have to understand that ferric ammonium nitrate can behave like this as well. Okay, so after this uh, concept, let us go to the manganese dioxide chemistry. So I have included two examples here, okay? And here also, like selenium dioxide or Fettigen's reagent, in this manganese dioxide case also, we have to come across some selectivities. So what are those selectivities? In the first example, you have two alcohol functionalities, okay? One of which is simply primary alcohol, and the second one is present in the benzylic position. So if you are given only one equivalent of manganese dioxide in presence of benzoyl peroxide, and the catalyst is adsorbed on titanium zirconium surface, you only have to focus on the manganese dioxide, okay, because this is going to do the oxidation reaction. So can any one of you guess which of these two alcohol functionalities would react if you are given only one equivalent?
Second alcohol, that secondary alcohols.
Yes, very good. When you
Yes, sir.
have this primary and benzylic, the reaction would selectively occur on the benzylic position. Okay, and if you want to say secondary versus primary, yes, secondary will go faster. Now let us come to the second example. Here again you are given two alcohols. One is primary and the other is secondary or benzylic. So if you look at this particular reaction, you will see the opposite way. The primary is preferably oxidized here. Why is it so? This is because you can see both these two positions are benzylic, okay? So when you have primary versus secondary benzylic, you have to get the selectivity rule in the opposite side. That is, in the first example, if you see, you have only one benzylic position, and you just have to simply oxidize that position over primary, because this is not benzylic. But when you have primary and secondary both in the benzylic position, you always have to go for the primary one. You can note down these points. When you have manganese dioxide reaction and you have two benzylic positions, one is primary versus secondary, you have to choose the primary one over secondary, and it is uh, experimentally accepted, okay? So thus these two examples will help you understanding how manganese dioxide adsorbed on particular metallic surfaces show selectivity towards various primary, secondary or benzylic alcohols. Okay, so after that, let us move to this manganese dioxide reaction. Okay, so again you are given the substrate which is highly functionalized. You have, suppose, ether functionality here, and then amide functionality here. Again you have ether. So various functional groups are here, but You don't have to worry. You only have to look at this allylic alcohol, because like uh, Sir Pan has discussed, manganese dioxide will always go for the allylic benzylic alcohol. So if you look at the product, you are given ester functionality at this position. That means in the reaction condition, not only manganese dioxide, but also sodium cyanide and methanol is also taking part. So let us discuss the mechanism of this reaction so that you do not have to worry about how you were supposed to get an aldehyde here, but you ended up getting ester. Okay? Always remember, when you are given sodium cyanide in methanol along with manganese dioxide, you have to follow this particular mechanism. So at first, like you can guess, you will get the desired aldehyde by oxidation with manganese dioxide. But since you have sodium cyanide which can ionize to Na plus and Cn minus, this aldehyde will not be stable under these conditions, and the cyanide nucleophile will attack the aldehyde quickly. So you get a cyanohydrine which is unsaturated in the alpha beta position. Okay, this cyanohydrine product you will get. Again, you are getting a secondary alcohol which is allylic, and you already have manganese dioxide in the reaction mixture. So that will act again to give you oxidation of the secondary alcohol. So you get oxidation of cyanohydrine to get this alpha beta unsaturated ketone. Now methanol is added in the reaction mixture. Now what happens? Methoxy anion will just simply displace this cyanide. Okay, you can just imagine OMe minus would attack at this alpha beta unsaturated ketone, and the Cn minus will leave from here. Okay, and in turn you will get your desired product which is alpha beta unsaturated ester. If you had only manganese dioxide in the reaction condition, you can simply oxidize your alcohol to aldehyde and leave it as it is. But when along with manganese dioxide you are given such reactive reagents like sodium cyanide, methanol, you have to go move. Yes, you have to move forward. Okay, in the aldehydic stage you cannot stop. So at first, if you look at the product, you may feel confused how the ester is coming. But if you go step by step by nucleophilic additions and substitutions, you can easily guess the final product, which will be your alpha beta unsaturated ester. So various organic chemists have used this strategy if they want to synthesize alpha beta unsaturated ester from allyl alcohols, because whatever the reaction condition is given, it is not interacting with any other functional groups. Okay, it is simply reacting only at this position, and you are getting alpha beta unsaturated ester. So after discussing with this interesting example of manganese dioxide, let us move to the next question. So this is an easy question from the topic desmartin per iodinate. So hypervalent iodine reagents have also been covered in this week's lecture, and DMP is a very good and very mild reagent for oxidation of primary and secondary alcohols. Okay, and it is comparable to Swan oxidation. whatever kind of reactivity you find in swan oxidation, you can guess same reactivity in desmartin per iodine reagent. In fact, DMP is a little better towards highly sensitive functionalities, okay? But you have to remember this DMP reagent is very expensive, okay? So if you want to cut down your expenses, you should choose swan oxidation. So in this question, you can see this again highly functionalized molecule is given. You have ester, amide, even Bock protected amine is also given here, and you have a secondary alcohol present here. So in this DMP reaction, if we go back to the lecture and remember the reaction mechanism, what happens? The substrate that is given to you would attack your hypervalent iodine, and you have three acetate groups which are very good leaving groups. One of these three acetate groups would leave after the alcohol attacks. Okay, so now this oxygen will be attached to this iodine and your acetate will leave, and you will get this particular product. Okay, now what happens? The alcohol has this alpha proton. Okay, this alpha proton. So this alpha proton will be extracted by a neighboring acetate group in the hypervalent iodine center, and in turn you will have deprotonation at this center, and the arrow moves towards oxygen, and this iodine oxygen bond will finally break. Okay, and this concerted pathway would lead to the oxidation of the alcohol into ketone. So secondary alcohols, when treated with DMP reagent, you get very excellent yield of the desired ketone product. Okay, and if you look at the byproducts, these are mild byproducts, non-toxic byproducts. You only get acetic acid and this iodine uh, byproduct. Okay, and both of which are non-toxic. So thus in your substrate which is given, all your other functional groups will stay untouched, and you will get the oxidation of your secondary alcohol into ketone. And if you look at the yield of the reaction, it is very high, which is 70% yield, and the reaction is fast also. Within 1 hour of your reaction, you are getting 70% yield of the product. Even NH-Bock and protecting group is also staying intact, okay, which is a very good thing. So with this easy question, let us move to the next question. Again from DMP, you have already gone through the mechanism, so you can easily guess what will be the product here. Can anyone tell?
Ketone. Not ketone.
Yes, simply you will get the desired ketone, which is again in very high yield, 77%, and here also O-benzyl protecting groups are staying intact. Okay, they are staying untouched, and you will get your desired ketone in 77% yield. So like I said, DMP is a very good reagent when it comes to oxidation of primary and secondary alcohols. More frequently used for secondary alcohol synthesis, and it is very good when you have sensitive functionalities, but the drawback is it is a little expensive. Then another example from hypervalent iodine section. Here you have IBX. Okay. Again, if you look at the substrate here, you can see TMS is present, which is containing carbon silicon bond, and then OTBS protected alcohols. Okay. So if minor amount of acid goes into your system, you can easily expect the breakage of these oxygen silicon bonds. Comparatively, carbon silicon bond is a little more stable than oxygen silicon, but these oxygen silicon bonds are very labile. Okay, they can fall off very easily. So what happens if we add IBX in the reaction mixture? You can see the mechanism follows a very similar pathway as DMP. What happens? Alcohol first comes and attacks at the iodine center, and like we saw in the case of DMP, the alpha proton will be abstracted from this position by this hydroxy, and you will get iodine oxygen bond breakage, which will give you ketone and iodobenzoic acid. Okay, so here also if you see, the byproduct is non-toxic. So if you look from toxicity point of view, IBX and DMP are good reagents. Okay, and if we look at the reaction, you can simply see the oxidation of your secondary alcohol into ketone without affecting OTBS and TMS groups, and the yield is also not bad. You can say moderate yield, which is 55%. Okay, so getting the desired product in hand without affecting your functional groups is the best thing. Okay, so thus we have discussed the hypervalent iodine section. Now let us go to another oxidizing agent which was covered in today's in this week's lecture. So you have a pentacyclic molecule here. Okay, do not get scared looking at the number of cycles. You just have to look at the functionalities present and the condition given. You are given aluminum isopropoxide and this ketone. Can you recall what are these conditions? Which reaction does these conditions follow? Can anyone recall? Okay. So
Organic
aluminum,
alcohol converted to keto.
yes,
Organic alcohol converted to keto. And cyclohexane converted to
yes. Can you remember the name of the reaction?
Marvin Pandroff Weldy reduction.
Okay, that is the reduction. And what about the oxidation reaction? What was the name of the oxidation? Okay, I will help you. So these are two reactions, okay? Openiver and like you said,
Oxidationases.
MPV. Yes. So very good. You have already remembered the MPV reduction, Marvin Pondor-Verley reduction. So these two reactions are related, okay? How they are related? When the oxidation pathway is followed, that reaction is named as Oppenheimer oxidation. And when the reduction pathway is followed, which is the opposite of Oppenheimer oxidation, that is called Marvin Pondor-Verley reduction. I think that reduction will be covered in next week's lecture. Okay, so you can go through that lecture. So this particular reaction, and very good, you have already guessed it correct, that this alcohol will be oxidized into ketone and the cyclohexanone which is given will be reduced to alcohol, which is very good. Okay, you already know the products. So if we look at the Oppenheimer oxidation reaction mechanism cycle, what happens? You have this aluminum isopropoxide, okay? And the alcoholic oxygen attacks the aluminum center. So, okay, after the attack, you will get this particular intermediate product. And if you look at the complete cycle, you will see the involvement of a six-membered transition state, okay? And this six-membered transition state has already been covered in the video lecture. Because of the formation of this stable transition state, you can say that open your oxidation pathway is followed, okay? So this transition state is actually very, very important in this reaction mechanism. So if you look at the final products of the reaction, you can expect that 65% of the substrate, you will get 65% yield of the reaction where the substrate is simply oxidized into its keto form, and you are getting the desired alpha beta unsaturated ketone. So in the standard reaction condition, when people follow open your oxidation, they use acetone, okay? Mostly people have used acetone, and in place of acetone, you might you may come across ketones of these forms, okay? You don't have to get scared looking at other ketones when they are given. You just have to know whenever you have aluminum isopropoxide given in presence of cyclic or acyclic ketones, you have to follow Opinier oxidation. And then let us move to this particular reaction, which is again a little difficult from whatever has been covered in the week 2 lecture, okay? If you recall the sodium metaperoxide reactions, these are the common reactions which are followed by the diol substrates, okay? When you have diol, you can expect the cleavage of the carbon-carbon bond of diol, and you get, if you have a cyclic substrate, you get diketones or dialdehydes, and if you have acyclic substrates, you will simply break this carbon-carbon bond and you get aldehydes, ketones, or two ketones or two aldehydes, okay? Like that, these kind of products you get whenever you have sodium metaperoxide. And in some examples, I have seen that you are given sodium metaperoxide with osmium tetroxide or ruthenium reagent, okay? And in those examples I have seen, you are not given diol, you are simply given alkene, okay? You can just imagine a carbon-carbon double bond here and no diol. And in reagent side, you are given sodium metaperoxide or and osmium tetroxide. In those examples, you have to form the diol first, and then you have to cleave the carbon-carbon bond alpha to the diol, okay? So those examples have also been covered in the lecture. You can go. So this example which I have included, if you look at the final product, neither you are seeing diol formation nor carbon-carbon cleavage. If you were given osmium tetroxide here with sodium metaperoxide, in place of Ki and azide, we would have simply formed the diol first, and we would have cleaved the diol to get two aldehydes. But here, no diol formation reagent is given, and if you look at the product, it will be very unexpected to you, okay? But do not worry, we will go through the reaction mechanism step by step, and this reaction also I have included in this tutorial because not necessarily sodium metaperiodate would always give you cleavage of diols. Okay, what will you do when you are not given diol or a diol forming reagent? And if you are given reagents like Ki and sodium iodide, potassium iodide and sodium azide, how you are going to get products like this? So let us look at the mechanism. What happens? Sodium azide can easily form azide radical, okay, which is a stable radical. And in presence of sodium metaperiodate, potassium iodide gets cleaved into iodine radicals, and you get combination of iodine radicals into iodine molecule. Okay, now you can see that when you have sodium metaperiodate in presence of potassium iodide and sodium azide, you get these two products in the first step, which is iodine molecule and azide radical. Then in the second step, if you look at, these two will get combined. Okay, this iodine, as you all know, iodine molecule can form iodine radicals very easily when it comes in contact of visible light. Okay, if you have iodine in a bottle in your lab and you keep it open for longer time, the iodine molecule can easily get cleaved. Similarly, in the second step, what happens? The iodine will cleave to give you two iodine radicals, and one iodine radical will get combined with azide to give you this substrate. Okay. Now, when you introduce your alkene to the system where you have this azide and iodine bond, you will see the formation of this stable benzylic radical. Okay, and then this stable benzylic radical will be immediately trapped by your iodine radical or iodine molecule. Of course, when it comes to iodine molecule, it will first get cleaved into two iodine radicals and it will trap this stable benzylic radical. Thus, you can see unexpected and exceptional reactivity of your alkenes when you have salts of potassium iodide and sodium azide are given along with sodium metaperiodate. So you don't have to memorize anything, you just have to know the concept. What happens when you are given an alkene with sodium metaperiodate in presence of these reagents? Okay, this is a kind of reactivity of sodium metaperiodate. So this example I have picked from a research paper which I found very interesting, and this type of reactivity is also shown by sodium metaperiodate. So now let us move to this question, which is from the DDQ part. Okay, so this example you may find a little difficult, but if we discuss it step by step, you will understand how DDQ is reacting here. Another thing I would like to tell you that in this week's lectures, I found that there were a lot of informations. Okay, all the three lectures had so much of information that you may get confused. Okay, so I would suggest just go through the video lectures one by one slowly, understand the concepts, that how the reactions are happening, how the mechanisms are going, then you will not find those reactions difficult. Okay, because so many reagents were covered in this week: DDQ, ferric ammonium nitride, manganese dioxide, selenium dioxide, then hypervalent iodine. A lot of reagents were covered. So, and also one more thing I have already told you at the beginning of this lecture, you can make your own notes while watching the videos. That will be very, very helpful to you. So again, this reaction is from DDQ part, where you can see you are given this aromatic substrate along with a aryl ketone in presence of ferric chloride and DDQ in dichloroethylene solvent. And of course, as you know that DDQ is an oxidizing agent and also it helps in aromatization, okay? But none of these reactivities is seen in this particular reaction. Rather, you see the introduction of the aryl ring at the alpha position of the ketone. So if we look at the mechanism, this is the structure of DDQ, okay? So if you look at the mechanism, first the ketone will react with your Lewis acid, ferric chloride, and your ketone will get activated by the Lewis acid, which is ferric chloride, okay? Okay, I would request you all to just mute the microphone so that it does not disturb the learners. Okay, so the ketone is activated by the ferric chloride and you get the enolization of your ketone, okay? So let us go through path A first, because going through both the paths may seem confusing. Let us go through path A first, A1. So we are introducing DDQ to this enol, okay? At this position, DDQ will get converted into this oxy radical, and in turn you get the oxy radical of your enol, okay? This oxygen iron bond is broken by DDQ and you get this radical. But see, whenever you have electronegative atom, you cannot place your radical at the electronegative atom. So this radical will quickly get converted into uh, I would request, can you please mute the microphone? Okay. So like I said, the radical you cannot place on the more electronegative atom. So it quickly gets converted into this benzylic radical, okay? Then it again reacts with DDQ to give you this carbocation, okay? Now your aryl substrate, which is 2A, this is your aryl substrate. So after the formation of this carbocation, this aryl substrate is introduced, which quickly traps your carbocation, okay? In turn, you get another carbocation which loses a proton to give you your expected product. Okay, this is how DDQ is participating in the reaction pathway where it is where it is giving you a reaction between aryl ketone and aromatic substrate and you are getting the trapping of the aromatic substance at this alpha position of the ketone. Okay, you can just go through this mechanism to understand how this kind of reactivity is shown by DDQ. Okay, along with that, DDQ can also show aromatization reaction and oxidation reaction, and examples of those reactions have already been covered in the video lecture. Okay, so this is another question, similar question if you see, where we are trapping this sulfone at this olefinic position. Okay, and what are the reaction conditions? You are given the sodium sulfonate, sodium iodide, ceric ammonium nitrate, anhydrous acetonitrile, and under argon atmosphere. Okay, so here see, anhydrous acetonitrile is your solvent, argon is just kept to maintain the inert atmosphere, and the reaction is carried out in 0 degree. The reagents which are participating are going to be your sodium sulfonate, sodium iodide, and ceric ammonium nitrate. And if you look at the product, you can see the trapping of the sulfonate at the olefinic position. So since you do not have any reactive functionalities like alcohol, which could have been oxidized by ceric ammonium nitrate, in this particular reaction, you see that you are getting trapping of this sulfone. So the mechanism follows a radical pathway. Okay, what happens? You have sodium iodide in the reaction mixture. Okay, so sodium iodide will get ionized into Na plus and I minus, and I minus will get converted into iodine radical by ceric ammonium nitrate. And of course, simultaneously you will see a reversible reaction, which is combination of two iodine radicals into the iodine molecule, which will also move to the backward direction. Okay, now you have another salt, which is sodium sulfonate, that will give you this anion, and like in case of iodide, you saw that ceric ammonium nitrate is giving you iodine radical. In this particular anion also, you will see the formation of radical on the oxygen atom. Now, this oxygen atom radical is in resonance with this sulfur radical. Okay, because if you compare the electronegativity of oxygen and sulfur, oxygen is more electronegative. So, it is better to place the radical on the less electronegative sulfur atom. Now, what happens? This is your reactive radical, which is going to get added to your olefin. Okay, and you have two possibilities in the olefin. If this sulfur radical adds here, you will get a primary radical here. Okay, and if this radical adds here in the exo side, you will get a secondary radical here. So if you compare the stability of primary versus secondary radical, the radical which you will get at the secondary position will be the more stable one. Okay, so the sulfur radical will get added this side, and you will get this secondary radical. After that, you already have iodine radical and iodine molecule in the system, which will give you iodine radical, and this benzylic radical will be trapped by iodine radical to give you this product. Further, this reaction will give you HI elimination, and you will see this olefinic product where you have this sulfone trapped. Okay, thus when you have this kind of substrate, you have to start your mechanism by formation of iodine radical and formation of sulfur radical with the help of ferric ammonium nitrate. And in these kind of reactions, ferric ammonium nitrate acts as a radical formation agent. In simpler words, it is acting as an oxidizing agent by converting the iodide and sulfonate into their radical forms. Okay, so thus whenever you have these kind of olefinic substrates and you are given sodium sulfonate salt, sodium iodide salt in presence of ferric ammonium nitrate, you have to trap the stable radical in olefinic position. Okay, and you may think that it can get trapped in this position also, but that will not be the case, because in the reaction mechanism we saw that the secondary uh, radical was more preferably forming. Okay, the benzylic radical, which is more stable, it was forming. So thus this is the product that you are going to get in this reaction. So with this we have already covered all the questions, and today we have covered 14 different questions on the topics which were covered in the lectures this week. Let us just go through all the 14 questions which have been covered today. First, we started with this easy topic, which was selenium dioxide. Okay, and we saw how selective oxidation of the allylic positions into allylic alcohols was happening. Then we came across this reaction where we found the formation of two different products, and I asked you to guess which one would be the stable product, which will be more in amount, and one of you, Sharad, answered that this will be formed more abundantly, which was absolutely correct because of the steric hindrance between these protons and this OTs. Uh, okay, I will ask again all of you to please mute your microphones so that it cannot disturb others. Okay, so yeah, one of you, who was Sharad, correctly predicted that this particular product would form in larger quantity, which is found to be 61%. Then we moved to this question, which was from TPAP oxidation, and we saw that although we had this highly reactive epoxide ring, we only got Ley-Griffith oxidation of the alcoholic group into the aldehyde, and the yield was also very good, which was only 12% in case of Swan oxidation. Then we discussed a few questions from Fettigen's reagent, and we also discussed the mechanism which is established on adsorption chemistry. Okay, and we saw how secondary versus primary selectivity was observed in case of silver carbonate silite reagent, which is Fettigen's reagent. And then whenever you had primary versus secondary versus allylic secondary, you had to go for the allylic one, like Reddy had answered correctly. And then we had this diol where we observed that one alcoholic functionality got oxidized first, and then due to the formation of stable six-membered electron ring closure was observed, and finally you got lactone because of the oxidation of this secondary alcohol by Fettigen's reagent. Then this question, which was a little difficult and different from the topic, and which was only included to show you how ferric ammonium nitrate in organic synthesis can participate in different roles. Okay, it can act as a Lewis acid also. Okay, so then we went to manganese dioxide oxidation. We saw whenever you have primary versus benzylic, you have to always go for the benzylic one, and if you have primary and secondary benzylic, you have to go for the primary benzylic one. Okay, so it may seem a little confusing to you, but if you understand the selectivity, you are good to go. Okay, then another reaction of manganese dioxide we saw, which was giving us alpha beta unsaturated ester. Okay, so why we were not getting an aldehyde? Only because you were given reactive reagents along with manganese dioxide, which were sodium cyanide and methanol. Okay, so this reaction pathway gave you the alpha beta unsaturated ester. Okay, so and two molecules of manganese dioxide was involved in the reaction mechanism. So by understanding the reaction mechanism properly, you can clearly guess how ester is forming from this allylic alcohol. Then we discussed DMP oxidation and why organic synthetic chemists choose DMP for highly functionalized molecules. That also we discussed, and you simply observe the oxidation of secondary alcohol. Again, in this reagent, we observed the oxidation of your secondary alcohol, and the yield was also very, very good. Then we discussed IBX, which is very similar to DMP. And here also you were seeing that OTBS and TMS groups did not fall off in presence of IBX, which is a very good thing. Then we discussed open-Eur oxidation, which is completely opposite to MPV reduction. And we saw here also no other functional groups were interfering, and we got simply oxidation of this allylic alcohol into alpha beta unsaturated ketone. And like you correctly pointed out, that this substrate in turn would get reduced to secondary alcohol. Then we discussed this radical pathway, which was given by sodium metaper-iodate, and we saw that when you do not have diol or diol forming reagent, you can expect this kind of trapping products in case of sodium metaper-iodate. And again, this particular example was also a little different from whatever was covered. So here also you could see that trapping of this aryl substrate happened at the alpha position of your ketone. And then lastly, we came across this ferric ammonium nitrate reactivity, which was a little different from the oxidation reactions covered in the lecture. And we saw that in presence of sodium iodide and sodium sulfonate, we can observe the trapping of stable radical on the olefinic position. So with this, we have come to the end of today's lecture. So if you have any queries regarding today's lecture, you can approach me in the upcoming tutorial. You can go through the study materials or video lectures again, and then if you find any query, you can talk to me. I'm there. And again, in the next week, next Friday 7 p.m. to 9 p.m., we are going to discuss the week 3 topics, which are going to be reduction reactions. Okay, so I hope you are finding these NPTEL course video lectures and tutorials helpful. So thank you so much for joining. Do feel free to approach me regarding any queries, and do not hesitate. Okay, thank you so much.
Yeah, thank you, ma'am.
Thank you, ma'am.
Yes,
Can you please share the video lecture? This one, today's presentation.
yes. Today's presentation will also be uploaded on the YouTube channel, and the link of your of that YouTube videos will be provided to you in the Swayam.
Through email or through the login portal, NPTEL portal.
It will be uploaded on the NPTEL Swayam portal actually.
Okay, thank you.
Okay. If you are unable to find, then I can help you in like I will show you which YouTube channel you can go to. But you first
Please.
go through the portal. Okay. There
Okay, sure,
you
sure.
should find. Okay. Thank you so much.
Okay, thank you. Thank you very much.